Don't Memorise is wrong about the real numbers. This 1 million view video is misleading people about what the badly named real numbers really are. It explains that real numbers are points on the number line. However, at no stage does it explain what a point is or what the number line is. This is like a teacher going into a Japanese for beginners class and saying, "Desu wa Nihongo no copula desu." The same thing with the statement about the number line. Since Don't Memorise hasn't taught viewers the language of mathematics, it's meaningless. What is worse, since the language of mathematics sounds a lot like English, people are fooled into thinking that they have learnt something. So, I'm going to tell you what a real number is as mathematicians define it. I'm going to start with basic concepts and build a little tower of them. The first concept is a set. This is the foundation on which mathematics sits. For our purposes, a set is a collection of objects. Our next concept is an operator. This is a thing that takes two values and returns a third. Examples of operators are things like plus and times. However, operators don't have to work with numbers. You can have a concatenation operator, which takes two strings of text and joins them together, or a paint mix operator, which takes two colours and returns the colour of the paint when they are mixed. Or even an after operator, which takes two actions and returns what would happen if you did one thing after the other. Magma. We can combine these two concepts together to create a magma. This is the lowest level of our tower to the real numbers. A magma is a set and an operator that operates on objects from that set and only returns objects that exist within that set. This is a handy property to have because we don't get into a situation where we add two numbers together and get a kangaroo. Mononoid. On top of the magma, we can construct a mononoid. A mononoid is a magma with a few extra restrictions: associativity and identity. Now, I have a real love of mononoids. They are a wonderful little structure. I could do a whole video on how brilliant they are, and I will. Mononoids have associativity. This means if you have a run of operators, it doesn't matter what order we do the calculation in. We will still get the same result. Also, a mononoid has a special value called the identity. When the identity is one of the arguments to the operator, we get the other value back. For example, with addition, the identity is 0. If you add 0 to any number, you'll always get that number back. For multiplication, the identity is 1. Same deal. Okay, here's another example of a mononoid. The set will be strings of letters. The operator will be concatenation, and the identity will be the empty string. So, we can concatenate two strings together and get a new string. If we concatenate a string with the empty string, we get the original string back. And it doesn't matter what order we do the concatenation calculation in. We still get the same string back. Group. The next floor up is group. A group is a mononoid where each object in that set has an inverse. If an object and its inverse are operated together, it will return the identity. For example, with the group whole numbers with addition, each whole number has a negative number, which is its inverse. And if you add a number to its negative, you get 0. The identity of the whole numbers is the set of non-zero rational numbers with the multiplication operator. If you multiply a number with its inverse, you get the multiplicative identity. The thing about groups is that an inverse undoes the operation. If you double something and then you halve it, you get the original number back. My personal favourite family of groups are the permutation groups. Say, for example, you have a wheel that rewrites letters into different ones. Then you can think of applying different wheels after each other as an operation that creates a virtual rewriting wheel. With a small number of rewriting wheels, you could create a large number of ways to rewrite the alphabet. With inverses, you could then undo the rewrites and get your original message back. This was one of the principles behind the operation of the Enigma machine. Indeed, Polish mathematicians, using their knowledge of group theory, were able to find a weakness in the Enigma machine and tell the British about it, aiding the Allied efforts to defeat fascism. Commutative group. A commutative group is a group that has the commutative property. That is, it doesn't matter what order the arguments are written in, you still get the same result when you apply the operator. Ring. A ring combines the concepts we built on before. It is a set that has a commutative group, called addition, and alongside it a mononoid, called multiplication, and they distribute. So, for example, you could have the whole numbers with addition as the commutative group and multiplication as the mononoid. However, rings don't have to be big infinite things. They can be small finite things. For example, you know how if you add two even numbers, you always get an even number? And if you multiply two odd numbers, you always get an odd number? Well, if you chart out all the interactions, you get a table just like this. What is neat is this little set follows all the ring rules, so you can treat it just like any other ring. Field. A field builds on a ring. The additive group remains the same, but the multiplicative mononoid is promoted to being almost a commutative group, but 0 doesn't have an inverse. Because 0 doesn't have an inverse, you cannot divide by 0. The rational numbers and the real numbers are both fields. However, there are also a lot of finite fields that get used in things like modern cryptography and error correction codes. When you look up and see a little padlock icon beside the URL, that means a finite field is protecting your watching of me. Ordered fields. We build on top of fields by giving them order. Each pair of objects in a field is either bigger, smaller, or equal. And it follows the expected behaviour. If A is bigger than B and B is bigger than C, then A will be bigger than C. These rules are getting super restrictive now, but we are almost to the full definition of reals. The complete ordered field. A complete ordered field is one where there is no gaps. But how do we define what a gap is with numbers? Well, let's start with an example. If you square the rational numbers, you can sort them into three subsets. Numbers that when squared are less than 2, numbers that when squared are equal to 2, and numbers when squared are greater than 2. When you do this, you notice that there is a gap. And this also gives us a hint on how we can define completeness. Let's start with the idea of an upper bound. A subset has an upper bound if there exists a number above which there are no elements within that subset. Now, a subset can have many upper bounds. Like I could say, humans do not run faster than 60 kilometers per hour. And that is an upper bound on human running speed. But humans do not run faster than 100 kilometers per hour is equally as true and is also an upper bound. The definition of complete is, if a subset has an upper bound, it must have a least upper bound. That is, there has to be a smallest possible upper bound. For our less than square root of 2 example, the least upper bound is root 2. The conditions required to be a complete ordered field is so restrictive, only the real numbers qualify. If something is a complete ordered field, then it is secretly the real numbers in disguise. The number line is a complete ordered field, so when Never Memorise told us the real numbers are points on the number line, what they really were saying is, real numbers are real numbers. But why does all of this matter? Why did I go to the effort of making this video? Well, to explain that, I'll need a whole other video. So subscribe for that, and while you wait for that video, you can discuss what your favourite mathematical structure is in the comments.